Okay, in this example, I'd like to review a solution technique called ANOVA. In ANOVA, we're capable of investigating two or more samples, and in addition to the sample, we're also allowed to analyze sort of what we call blocking factors, which is a second factor. You can think of it as a row header if you'd like, where maybe the first factor is a column header. Okay, let's go ahead and take a look at this problem. We have Martin Motors. Martin Motors has a stock of 3 cars of the same make and model. The president would like to compare the gas consumption of the 3 cars, labeled A, B, and C, using 4 different types of gasoline. For each trial, a gallon of gasoline was added to an empty tank, and the car was driven until it ran out of gas. The following table shows the number of miles driven in each trial. So for this particular type of investigation, we're going to use a 5% significance level. And the questions that we're going to determine from this data is there a difference among types of gasoline? And finally, is there a difference between cars? So essentially we have 2 things going on. All of our cars are quote-unquote the same make and model, A, B, and C. And we want to make sure that all the cars are actually equal. That's what we would expect, that one of them is perhaps not a lemon. And the other type of question, well, we want to understand is there a difference between gas? Are we getting better performance out of, let's say, an 87 octane versus, something else, a higher octane perhaps? So anyway, that's what we're going to investigate in this problem. Let's go ahead and open up the starting file. Okay, here's the starting file. We have all of the types of gasoline going to be used: regular, super, unleaded, and premium. And we've recorded the mileage performance in terms of the 3 cars, A, B, and C. So let's go ahead and start this analysis just by describing the steps of our hypothesis testing procedure. Let's go ahead and document that here. We have steps 1 through 5. We have step 1, 2, 3, 4, and 5. And the description for these tests I'm going to document here. And I'm going to actually provide us a little bit more space for the description. Okay. And it's always a good idea to just review these 5 steps when you're starting this type of process. So let me go ahead and just finish this formatting. All I'm doing is just providing us some space for the text. Step 1 is to state the null and alternative hypothesis. Okay, so let's go ahead and do that down here. Let me grab some format just to make quick work of this hypothesis. We'll have H0 and H1. And in terms of the null hypothesis, what we're actually saying is that all of the means are equal. So mu of A equals mu of B equals mu of C. Now this is all in terms of the miles driven for that gallon. And the alternative hypothesis is that at least one mu is different. Okay, so that's the first step. That's the first rule that we need to follow. Okay, what about the second rule? Second rule here is select a significance level. We've already done that by selecting alpha as 0.05. Okay, so we have that documented. What is step 3? Step 3 is determine the test statistic. Okay, so we have the test statistic for this particular exam is going to be the F test. Okay, so unlike the previous techniques that we've explored, what we really want to do here is test the variance, which is going to provide some insight as to whether we can conclude that the means are equal or not. Okay, step 4, formulate the decision rule. In other words, based on the test and critical statistics, when can we say that we are going to fail to reject null or accept the alternative? So in terms of that, let's see, we have 2 different rules that we can basically say. The first rule is that we are going to reject the null if the F stat is greater than F critical. Otherwise, if we fail to reject null, this is a situation where if F stat is actually less than F critical. Okay, so these are really the only 2 possibilities. Either we're going to reject null and accept the alternative, which maybe I'll change the order of this. Maybe this makes a little bit more sense and is consistent with the way we wrote out the null and alternative. So essentially what I'm saying here is if we fail to reject null, we're going to quote-unquote accept the null hypothesis. And that will only come if the F stat is less than F critical. That means our F stat is to the left of the decision boundary created by the F critical. And if we actually have enough information to reject the null, which also means we're going to accept the alternative, and I'm just going to put aka accept alternative, that's going to be a situation where F stat is actually greater than, and I'm going to erase that is. So these are the 2 rules. Now let's go ahead and take a look at our formula sheet just to review these concepts. Okay, the F distribution looks like this essentially, and we're in the rejection region if we're to the left of the decision boundary that is defined by F critical. Now if F stat is actually greater than this F critical, we're in the rejection region, which relates to the null. So we can accept, in other words, the alternative if we're in this region over here. Okay, so I'm just going to copy this figure here and just put it in our Excel spreadsheet just as a reminder. So let's place that right here. Okay, now we're down to step 5. So this is all about the sample information, which really has been done for us, but these are the general steps that you go through when you want to make a conclusion about your sample data. So select a sample, which again we've already done, perform the calculations, which we'll let the data analysis toolpack do, and finally make a decision. Okay, so let's go ahead and perform that test. Let's go to Data, Data Analysis, and we know this is going to be a situation for ANOVA because we have 3 samples. So that's definitely more than 2. So we can't conduct a Z or T test. What we need to do is analyze a variation to make a conclusion about the means. So now we have to decide whether we're going to run a single factor, a 2-factor with replication, or a 2-factor without. Now, in terms of the factors here, we have 1 factor being the cars, and actually another factor being the type of gas. So this is a 2-factor analysis. Now we have to decide, is it a situation with replication, or is it without? Now, what replication means? Right now, we do not have replication. If we had, let's say, 3 rows in a row of regular, 3 rows in a row of super, 3 rows of unleaded, and 3 more rows of premium, and we collected information with all of those, we're replicating the times that we have, let's say, regular with A, regular with B, regular with C, and then perhaps another row of regular A, regular B, regular C, and then another regular row of A, B, and C, followed by all the 3 combinations of the super. That's what replication means. Here we have a replication of 1, if you will. So that's a situation where we would say it is without replication. Let's go ahead and hit this test. Our input range is going to be the entire table. We do have labels. Our alpha is 0.05. And I'm going to place this report right here under our rule. Let's go ahead and hit that test. Now let's take a look at the information provided from this test. We have information regarding the gas type, the counts, the sums, average, and variance. Same thing in terms of the statistics calculated for the types of cars. And then we have the most important part about this table. Now we have information that is basically summarized in Excel by rows, by columns, and by error. Now if this was a single factor test, we'd have within groups and between groups. Now that's not necessarily what we have here because we have more factors. By rows is actually referring to how your data is organized. And our data, so we have the type along rows. So this is going to be gas type. That's where we're going to get all of our information from to make a conclusion about the gas type. Okay, and just to continue this, columns in our data set is represented by A, B, and C. So columns here is going to be about the cars. Now we don't have to necessarily worry about this error associated with this. That's a little bit beyond the scope of this video. One thing I failed to actually document is that we have 2 sets of null and alternative hypotheses. So what I'm going to do is, one, we have a hypothesis about the cars in terms of the mu, the average for the cars. And then we also have a secondary set, so I'm going to move this up here just a little bit and go ahead and insert, let's insert 3 rows here. And I'm going to actually insert 1 row above our initial hypothesis. This is all about the cars. So I'm going to document this as car hypothesis test. And let's go ahead and just merge and center this range so we can keep this information straight. Now we also have a situation where we are testing a hypothesis about the gas type. So actually, to keep this format, I need to insert 1 more row. So let me do that. And I'm just going to copy this statement here and actually paste it here. And here we have the hypothesis about the gas. Now here, mu of, let's just remove these values here in this cell. Here what we're actually saying is the mu of, let me look at the types, regular is equal to the mu of super, is equal to the mu of unleaded, is equal to the mu of premium. The alternative hypothesis is the same. At least one of these mu's is different. It could be a situation where mu of regular is different than mu of premium, or maybe regular, super, and unleaded are all statistically equal, but premium is not. So we don't know which one is different, so what we're going to conclude is that at least one is different. Okay, so now we have all of the hypothesis test written out, and the rule exactly follows what we had discussed prior. But we'll have 2 situations to investigate. One hypothesis test for the car, one for the gas type. Okay, so let's go down here and look at the results again. If we were to make a conclusion about the gas type, what we're saying is there a performance difference based on isolating the effect of gas? So we'll have a conclusion here, and I'll just document about the gas. Okay, and let's write out our conclusion. Whoops. Here. The conclusion is that our F stat is actually to the left of F critical, which, if you get familiar with this test, we know that that's in the fail to reject null. So let's go ahead and write that down. We fail to reject null, which means that in terms of the gas type, there is no difference in gas type. Okay, that might seem a little odd, but that is exactly what the information is telling us. And if we were to draw this out in a generic sense, what we have here is an F distribution. Let's assume it looks something like this. We have an F critical value here at F4. So I'm just going to say, well, let's just document it as F critical. And remember, this is an alpha of 5%. And the F stat, I'll just document here, is pretty far away from that. So we have a value here, and of course we have our line that defines what our decision will be. Since F stat is to the left, we are in the fail to reject region. If we were over here, it would be reject, but that's not the case. So our F stat is telling us we're going to fail to reject. If we fail to reject, we are stuck with a conclusion that relates back to our null hypothesis. They are all the same. We didn't reject this premise. There simply wasn't enough information to tell us that the performance difference related to the gas is statistically different. So they're all the same. Now, what about the car type? And I'm just going to copy that to save some time. So car. Is there a difference between the car? Do we have one that just outperforms all other? Or maybe two that outperforms one? Is there a lemon perhaps? Okay, let's look at those results. So we're in the column information now. Now if I look at the F value, I see that we have a very similar situation. Our F stat is less than F critical. So what I drew here exactly applies. Of course the numbers are different, but the only thing we care about is the relative location of each, essentially to make this conclusion. So I'm going to conclude that I'm going to fail to reject the null. There is no difference in the cars. Okay, another way to look at that is simply look at the p-value. Here we have extremely high p-values, which essentially can be compared to our alpha value. Anytime we have a p-value that is lower than alpha, we can reject the null and accept the alternative. We don't have that situation here. We have a situation where our p-values are extremely high, which represents a case where we're in the fail to reject region. And let me just demonstrate that by this graphic here. The p-value would actually be calculated. Let me try to draw this a little bit better. The p-value would be the area to the right of this F stat. So it would be actually the whole entire area under that's highlighted here under the curve, where the alpha value, remember, was calculated here. So it's saying basically that your p-value is far greater than your alpha value. So we're making the same conclusion. You will always make the same conclusion about this hypothesis, regardless if you interpret F stat versus F critical or just the p-value.